Antimatter, the mirror opposite of the world we live in. When matter meets its twin, they vanish in a flash of energy. A tiny mass, a colossal release. E equals mc squared. Antimatter isn't sci-fi. It's used in medicine and imaging today. But making it, storing it, and understanding it costs immense effort. A gram of antimatter would cost far more than we can afford. In this video, what antimatter is, how we found it, how we make it, and what it might do. Let's start at the beginning. What is antimatter? Welcome, this is antimatter. Antimatter is made of antiparticles, partners to ordinary particles. They share mass but have opposite electric charge and quantum numbers. Baryons and leptons have mirrored numbers. Protons +1, antiprotons 1. When a particle meets its antiparticle, they annihilate. Electrons and positrons produce 2 gamma photons, each 511 keV. Higher mass pairs create photons, neutrinos, and particle showers. The energy release follows E equals mc squared. Tiny mass, huge energy. Experiments show antimatter falls down. Gravity treats it the same as matter. Spectra of antihydrogen match hydrogen within experimental precision. CPT symmetry predicts identical masses and lifetimes. So why don't we live in a universe of equal matter and antimatter? The early universe should have made both, but something tipped the balance. Physicists call the mystery baryogenesis, one of the big unsolved problems. Later we'll cover candidate mechanisms and experiments trying to solve it. First, a quick look back at how antimatter entered physics.
More carrots. Don't tear it. More carrots. Where's Garrett?
Vegetables. Vegetables.
Here it come from the west side. The left side. The right brain.
Ideas of negative matter predate modern physics. Early ether theories toyed with opposites. Arthur Schuster coined the term antimatter in 1898, imagining anti-atoms and anti-solar systems. In 1928, Paul Dirac wrote an equation that hinted at anti-electrons. Mathematically, the solutions implied partners to known particles. Oppenheimer helped interpret Dirac's math. The idea of a positron followed. In 1932, Carl Anderson discovered the positron in a cloud chamber. Soon scientists imagined a full periodic table of antimatter, anti-atoms mirroring atoms. Feynman and Stuckelberg offered a useful picture, antiparticles as particles going backward in time. That interpretation is a tool for calculation used in particle physics every day. As accelerators advanced, antiprotons and antineutrons were observed. Today, labs like CERN produce and trap antimatter for precision experiments. Collaborations form to create and cool antihydrogen for study. Next, how we find, make, and store antimatter. Antiparticles are born naturally in high-energy collisions, cosmic rays hitting our atmosphere. Satellite instruments detect positron signatures from thunderstorms and galactic centers. Even Earth's Van Allen belts contain tiny populations of antiparticles. In accelerators, high-energy beams strike targets and produce antiparticles in showers. Recent experiments use the SPS to create huge numbers of electron-positron pairs. For example, a single experiment yielded over 10 trillion pairs. Ultra-intense lasers can also create dense positron bursts from heavy targets. Antinuclei like anti-deuterium and anti-helium have been formed in collisions. CERN produced hot antihydrogen in the 1990s, later cooled and trapped it. Charged antiparticles are held with electric and magnetic fields. Neutral antiatoms use magnetic minima. Alpha trapped hundreds of antihydrogen atoms, some for minutes, a major milestone. Antimatter annihilates on contact. You cannot store it in ordinary containers. Traps need ultra-high vacuum, magnetic bottles, and precision cooling. Even with modern machines, producing a gram of antimatter would take astronomical time. Estimates put costs at billions to trillions per gram. It is currently the costliest material known. Researchers have proposed magnetic scoops to harvest naturally occurring antiparticles in belts. Records exist for storing antiprotons for over a year in precision traps. Space experiments search for heavier antinuclei that would signal large antimatter regions. AMS reported tentative anti-helium events, signals that require careful verification. Now, practical uses, speculative fuels, and the big ethical questions. Everyday applications exist. PET scans use positrons to image metabolic activity. Antiprotons have been studied for targeted cancer therapy in experimental settings. Positron emitters are also used for industrial imaging and material studies. Antimatter offers unmatched energy density, ideal in principle for deep space propulsion. Energy per mass outstrips chemical and nuclear fuels by orders of magnitude, but annihilation yields neutrinos and neutral particles that are difficult to use for thrust. Proposals use magnetic nozzles to direct charge decay products, still highly speculative. Antimatter has occasionally been discussed as a weapon trigger. The ethical risks are enormous. Large-scale weaponization is currently infeasible due to production limits and cost. At present, we simply cannot make or store enough antimatter to be a practical weapon. Back to the mystery. Why did matter win out over antimatter? Candidates include CP violation, baryogenesis processes, and out-of-equilibrium dynamics. Precision experiments compare particle and antiparticle properties to test fundamental symmetries. Space telescopes and particle detectors continue the hunt for cosmic antimatter. Antimatter is real, rare, expensive, and scientifically priceless. If you enjoyed this deep dive, subscribe for more science explainers. The antimatter question ties to the deepest mysteries of the cosmos, and the search continues.